I
Started.
मैंने ऐसा कभी किया नहीं है, इसलिए मेरे को इसमें आए कि बेसिकली हमने एक अलग ही डायमेंशन में देखे उसको, थोड़े कम डायमेंशन में, नहीं सेम ही डायमेंशन में,
तो एक बार
वही स्पेस अलग हो गया।
स्पेस अलग है। नंबर ऑफ डायमेंशन स्टिल रिमेन द सेम।
नंबर ऑफ डायमेंशंस
इसमें डी डायमेंशन थे, ठीक है ना, इसमें भी तेरा x1
it's already 5:40, so we'll start. Today, I'm going to review a set of 3 papers. The first is Alpha Evolve, which came out just a few weeks ago. And so we'll start with Alpha Evolve. We have an AI co-scientist that also came out of Google research. So Alpha Evolve is by DeepMind. AI co-scientist is a product that Google Research has come out with, and both of these are white papers. They're not published papers. So one thing you'll notice is we'll have to take a lot of leaps of faith, and the technical details. This is not something that you can replicate. This is just a bunch of ideas that worked for them. So there's a lot of explanation as to why these worked and what did not work, and there's not a lot of evaluation studies that you figure out why they did exactly what they did. But I think still a very revealing set of protocols that they have come up with to essentially make scientific and algorithmic breakthroughs. So by breakthroughs, I don't mean, so till now we've been used to co-pilots and agents which assist us in some task and also can do a few human level tasks automatically. So maybe small functions, code bases, PR reviews, stuff like that. But the emphasis of what I'll talk here is to actually make breakthroughs in terms of science and algorithms to reach either state of the art or to beat state of the art method. So what is the path that you have to take to achieve that? The path to, let's say, good reasoning and achieving good performance on reasoning and coding benchmarks can be through reinforcement learning, which you've seen with DeepSeek, and also then a lot of other players incorporating post training using reinforcement learning to get more reasoning abilities. But this is a significant departure from that paradigm where you're not really doing so. Any of these papers, they're not really touching the base foundation model. There is no training going on. So the Google papers exclusively use Gemini, and they use Gemini 2.0, not even 2.5, and they don't touch the foundation model. They take that as a given. The paper by people on DGMs also uses by Sakana AI. So this also uses O3. So one of the things that is very remarkable is they don't think about touching the foundation models. They completely rely on test time scaling, which is, can you figure out a way to iteratively improve on hypothesis? So how the scientific method works is you have a bunch of hypotheses. Let's say we all meet, we have a bunch of hypotheses. Some of these are promising. We experiment, then we learn something. From those learnings we come up with new incremental hypotheses, and this process goes on till we make a breakthrough. So Alpha Evolve, you can think of it as like this process being run multiple times across compute and running as long as it has to till it achieves a breakthrough. So it's basically an extrapolation of the scientific method that we use to come up with discoveries, but it does it completely autonomous in a completely autonomous way. So these are some of the remarkable achievements that Alpha Evolve has been able. So Alpha Evolve is basically an agent for scientific and algorithmic discovery. It's a completely autonomous system, so it's not an assistant, right? It's a system where you tell the system what you really want, and we'll come to what the contract is. But basically, it was able to develop a more efficient scheduling algorithm for Google itself, which released a lot of their resources which were being underutilized uh, to the tune of 1%. So 1% underutilization was reduced on Google scale. So that's huge. They were also able to figure out a new algorithm for matrix multiplication. There was previously an algorithm that was discovered by a mathematician that this is the minimum number of you need to do in, let's say, for every x by x, so 3 by 3, 4 by 4, there is a minimum number of scalar operations. For 4 by 4 matrices, that was 49 for a long time, for the last 50 years. Alpha Evolve was able to come up with a way to do it in only 48 scalar multiplication. So there are a few breakthroughs. Strasson's algorithm, right? So it provided an improvement to the Strasson's algorithm. So almost like there were a bunch of tasks. Almost on 60 to 70% of those tasks, Alpha Evolve was able to match the SOTA. 10 to 12%, it was able to beat the SOTA, coming up with completely new algorithms, and only on a few it was underperforming the SOTA.
You can also try the system or it's accessible.
No, you can't try the system.
So that's why you cannot test it.
Yeah. So basically it's an LLM code super optimization agent, right? And I think where we should really start is this diagram. So this is essentially tells you what the contract is between you as a scientist or an engineer and Alpha Evolve. What you need to give is what is the problem that you're trying to solve, right? So in the form of a prompt, right? What are the base foundation LLMs that you're going to use? So it's not going to train anything on its own, but they say that the system works better with better LLMs, but the best LLM they use is Gemini 2.0, right? And they use both, I think, Flash and Pro, but 2.0 is where they're at. And this is the essential part. So you have to be able to provide an evaluation code. So if it comes up with a solution, there needs to be a closed form, a code which it can feed that solution in to get some sort of evaluation. And so this is critical. And this is where basically your input, this is the most important thing that you will do as a scientist or an engineer, is provide this evaluation code, right? And you can also provide an initial set of programs which you feel are promising, right? So this is basically what you need to provide. What Alpha Evolve will do is basically, this is the pseudocode for it. So what we'll do is, it will have for any, so I'll briefly touch upon what evolution algorithms are. So evolution algorithms mostly work on the same premise that evolution as a system is how a species evolved. It uses that same paradigm to come up with better and better solutions. So a lot of times, like I've seen this being used for hyperparameter optimization also. So wherever you have some sort of evaluation function that is there, that's probably not differentiable, but you need to you can evaluate that function, you can get a score. And so how do you come up with better and better solutions? So what you can do is, you start with a first set of solutions, you call the evaluate function, you get set, let's say, the scores for each. Then you look at the top few promising ones and you mutate them. And mutation here means doing just slight tweaks. So what is really happening here is that you have a parent program. So let's say I gave it only one program. What it'll do is let's say we are somewhere in the middle. So it would have generated some programs and evaluated, stored them in a program database. Currently there's a parent program. From the database, I'll fetch whatever previous programs I've evaluated. Together, these will be the inspirations. This will be the parent program. And there'll be a prompt sampler. Let's call this an agent. The prompt sampler will look at the parent program, which is the current program. It will look at what has worked in the past, which is what is inspirations, and come up with a diff, right? So the initial, whatever parent program code is there, it will suggest a diff to that code. That diff will be applied, and then the evaluation will be run on the child program. The child program will be added to the database, and this will keep on going.
When you think he is able to look the past, so past, like how?
So
can the examples feed?
Yes. So let's look at. I think this is a good time to look at something like this, right? So every time, so this is the prompt to the prompt sampler. So the prompt sampler's job is, these are all the prior promising programs, and these are the scores, right? So this is a simple ML task, right? We might have given some, so this is how you initialize. So what you do is, you give in a program, you explicitly mark which parts of the program can be evolved. So that is within the purview of the agent. This is the initial sort of prompt that you give. No, rather the initial prompt is not here. So this is what the prompt sampler will get. It will say that this is the prompt that you will give. You are an expert software developer, yada, yada, yada. This is all what you will give. it will then add the prior promising programs along with their scores into the context, right? And then it will ask that this is the current program, these are all the previous programs, this is the overall prompt, come up with a diff, suggest a diff for this current program, and this will come up with a diff, right?
So basically, instead of like when we are using for hyperparameter optimizations, now basically it tries all of them and then gets the best one. Here
Yeah.
actually he will have some understanding of
What has happened previously. So the closest parallel to this is reinforcement learning, where an agent learns from experience, right? You could have, so probably they could have, what they could have done is an action is basically the diff that you're suggesting, and the reward is basically whatever the next evaluation sets is. But why change the model or do all that when the learnings can be condensed into the prompt? This is, I think, the key insight that without tweaking the foundation model.
But isn't that there a very big assumption over here that an optimal prompt exists? That is a very big assumption over here, right? Let us say that your base model is, now this is for coding, it may have been trained a lot on coding, and it is maybe an optimal prompt exists which gives you the optimal code.
Yeah.
But let us say there is some task for which it is not entirely trained on. Over
Right.
there, even if you give this diffs, I don't think mathematically we can say that this should hold.
Yeah, no, so I agree that first of all these systems, even by reading the paper, you will find that the first feeling you'll get, they're very fragile. It is very fragile. But the good thing about this is you're not using it to write production grade code. You're using it to solve like really hard problems. If it doesn't get solved, that's fine. But if it does, and it's a verifiable thing. So the existence of an optimal policy might not be there, but the existence of an optimal solution which beats the state of the art, that you can verify.
Okay.
Right. So the approach here is if you can maintain enough diversity and if you can scale in test time and come with iteratively improving solutions, there is a clear bar that is there and you can cross that bar and you'll know exactly when you'll cross that bar. So there's no question of what is the optimal policy here, where you know that there's a solution that you can beat. And as long as you can put in all the context, all the previous learnings into the into sort of the prompt, you probably don't need to train the model for a specific task.
So are they suggesting a recipe to kind of do this stuff, or is it like something where you have to iterate on top of your prompts and?
So they claim it's a recipe that because they have been able to demonstrate this on like 60 to 70 really tough problems. So they are claiming that this is a recipe, but it does depend a lot on, and we'll see that this is fairly subjective. For example, I think I'll get back to this question. But let's see what this is. So I've already showed you what the pseudocode is, and we'll go over these components one by one. So Alpha Evolve is basically a coding agent which orchestrates this autonomous pipeline and makes multiple LLM calls to address a very specific user-defined task, right? So as part of the task specification, you have to give a prompt, and these solutions have to be machine gradable, and you have to provide a mechanism for automatic evaluation of any solution that has been proposed. So this is again the key point. Again, you can explicitly mark what parts of the code that you want to evolve, right? And you can also provide really good priors. So any solution that you think a heuristic solution that works, that can be part of the first set of programs that you suggest to this, and it heavily influences where the program goes. And that's where some of the sort of instability comes, is that it is fairly dependent on how you start and how you even formulate the problem. So you have a lot of flexibility in choosing the abstraction. So for example, there are many ways to solve a problem. What I can say is, for example, one of the problems that they solve is how to route a incoming job. So Google has a massive cluster of compute. Now there will be incoming job which will have some compute requirement, some sort of CPU requirement and some memory requirement. Given that, what is the optimal way to route it? Now this is a very open-ended problem. What they do is that they say, don't tell me what the optimal this thing is, come up with a ranking function so that I can rank all the current hardware that is available based on the optimality for this particular job. So the task then becomes coming up with a intuitive ranking function. So the way that you pose this problem, so when they pose this problem in a completely open-ended way, it was not able to solve it. But when you pose this problem as only coming up with the ranking function and then allocating the particular job to that cluster which has the highest rank, it was able to improve whatever they were doing previously by 1%. Right? So how you ask for a solution is also very important. So this is what they claim is that for problems that are have a highly symmetric solution, so mathematical problems where you're trying to, it's one of the problems that they solve is I think the kissing spheres problem where you have to figure out in n-dimensional what are the maximum number of, if you have a ball at the center, what are the maximum number of touching balls that you can fit, right? So that's something that's very mathematical. You have to come up with a structure, and there you can ask for something like a constructor function. You don't need to explicitly ask for the answer. You can explicitly ask for a constructor function. In some places, you can just ask for the answer in string representation, right? What is the answer, right? Until you get to the right string, you don't stop, right? So different ways of formulating the problem they found to be effective for different kinds of solutions.
So they're saying that it can potentially lead to new scientific discoveries.
Mm-hmm. Yeah.
It's a little scientific is a little big term we use there, but it's like because in your particular example, you may find a good solution for this constrained setup, but it doesn't necessarily get extrapolated to a theory.
So this was one. So they separate this into two. I think scientific discoveries are part of the problems which are actually open mathematical questions. So for example, as I described the kissing spheres problem. So that's actually, you could claim that's a scientific discovery because there was no mathematical structure known that could have that many kissing spheres, but they came up with one. So that's a mathematical breakthrough.
Did it solve it for n equal to 4, n equal to 8 or any
11.
11.
Yeah.
And how much time does it take on average?
So they've not come up with like a list of exact time taken for each problem, but I think for the Google listening problem, I think it took 2 days for them to come up with the solution. So it was running continuously for 2 days. So there's no estimate of what compute hours, how many GPUs, all this stuff is not there.
That's why they're solving the biggest problem.
Right. Another thing they do, so apart from evolving programs, they also evolve prompts. So your initial prompt of how you wanted to solve the problem, that is also evolved over time to see if maybe you have not formulated the problem the right way or you've not used the right words. So you also have an option to evolve the prompt itself. Right? So it will maintain a database of all the prompts it has used and figure out which are the most promising prompts also. Right?
So in between ये सब चलता रहेगा, like when we are saying 2 days तो like वो prompt भी change कर रहे थे.
हाँ, so it's evolving the prompts, it's evolving the programs also.
Till it get the best answer.
Right.
The should reach like now we cannot move further.
Yeah. And one of the interesting things, yeah.
Like this kind of thing, is it like doable by anyone, or are they using some huge compute or something? Like, could I have also done this basically by just prompt engineering and stuff like?
Sorry, I didn't.
Can we replicate this thing like?
Yeah.
Like what things they are using, kitna compute?
Like they are not fine-tuning the model or anything like that.
Yeah, they're not fine-tuning the model or anything. It's all test time. Like basically, it's all prompts and responses in the end of the day.
So it's doable by anyone, right? Without any extra compute, I guess. Like
compute as in you don't need any training compute. I'm not sure how much how much inference time compute are they using. Yeah, right. No, for these tasks they have given the prompts. Like जो भी उनने ये किए हैं, they have actually come out with in the appendix. You have all those prompts. So theoretically, you should be able to replicate at least these problems exactly.
Nice.
Another interesting thing is so what they found is when the evaluation function, so generally even in reinforcement learning, the biggest constraint is the reward has to be a scalar. So you only have to have a scalar reward. So if you have multiple objectives, you condense them down into one, and that's how it works. Here, what they found is because you are basically putting everything in the context, you could have multiple evaluations, and they found that having multiple evaluations provides the agent more flexibility to approach a solution. So maybe the evaluation that you care about the most doesn't have a high resolution. So between 2 or 3 mutations, it doesn't change much, but there might be a secondary metric that shows a lot of variance, and that might show you the direction, whether you're moving in the right direction or not. So in general, they said that you have, even if one particular metric is of interest, having multiple metrics actually helps, right? Yeah, and this is the evolution part. So they don't say a lot. So I think one of the most interesting thing for me was the evolution part. How are they managing the evolution part? They don't say a lot. What they say is that this database and sampling from this database, that is I think one of the core parts of this algorithm. And they've not said a lot, but what they say is that we store these programs in this database along with the evaluation metrics. And they have mentioned a couple of evolutionary algorithms. One of the algorithms is so island evolution, where what you do is you have an initial set of random programs. Each of them is allocated an island, and then uh, programs within an island keep on evolving. They look at each other's code, right? So they can take inspiration from each other. And every, let's say, 100th round, you have a crossover of the best species from each island. That way, what happens is you have individual heuristics that get built. So different types of heuristics can get built on different islands independently. And then every sometime you have crossovers when heuristics can crossover. And why this is interesting is that what it says is that you don't want to cut off a chain of thought very early, right? You want intuitions to evolve because you don't know when this will come in handy, and this theme will come again when we go to the DGM paper. Is that you really want to have your options open till the very end, right? And the reason they're using this evolution approach is you really want to have a lot of diversity, because you can have this cross learning. So even though some heuristics might not be able to get to the end point by themselves, but when you develop a lot of heuristics independently to a good degree of sophistication, a crossover then might be able to cross the bar, right? So they use a couple of, so what they've exactly used, they don't know. They name a couple of evolutionary algorithms. So one is obviously the island algorithm. The other is something called a map elite, where what you do is you also come up with a way to quantify behavior. So let's say you have 10 different types of behavior identified. Every program is classified into these 10 buckets. And then every time you sample the elites from each bucket so that you have fair representation, right? And then
Quantify the elites.
by the evaluation metrics. So you have a quantifier not just for the evaluation, you also have to provide in quantifier for the behavior. So let's say I have a quantifier that this kind of behavior falls into this bucket. Every time you sample the elites from each bucket, you mutate, and then the new set of programs are again look at their behavior and again allocate to the
And it gets re-ranked also.
yeah, it gets ranked, of course. Yeah.
Very fundamental question. Sometimes what happens is that in order to get to, let's say, an optimal result, it is not about generating a newer version of the program. It's just about exploring the space more and more continually.
Yeah.
For as many combinations as possible. So there is not much of evolution going on as much as competition. I mean, you could not tweak the program enough to get to the right answer.
Yeah.
Or evolve it a lot to get to the right answer. You just have to keep searching that space.
Yeah.
And those problems, which are mathematically the most difficult problems to solve, how much of this would hold?
No, that's a good point, and there's an argument to be had there that this in fact all these three papers emphasize on incremental progress, right? Figuring out heuristics and incrementally mutating those heuristics compared to, let's say, one shot stuff. Like I think what you're talking about is like go for the moon directly in one shot, right?
Exactly, but I mean, untenable problems.
Yeah, so basically untenable in the sense that you can't take inspiration from a lot of these mutations, like those sorts of problems you're talking about, right?
The path is pretty clear. It's just that you have to spend a lot more time searching within that, let's say, dimension to get one aspect of it.
Yeah, I think something like this would work there.
So what evolves? I mean, I think a simpler question to ask is that, yeah, is there a way to understand what is it that actually evolves through these stages?
So basically,
Is it fundamental logic?
no, I think you were trying to say something like this. We have gradient descent where, like we start from somewhere, we take the differentiation and then we take a step in that direction. Like what are we tweaking over here is basically it's asking like because the model is the same.
The model is the same.
Now the first one that I raised was there exists an optimal prompt. So why not if it already exists, why can't we directly reach over there? Like, what are we changing in every iteration?
Yeah.
Is it the set of negative examples that are coming along is helping it out?
So what you're trying to change is basically code. At the end of the day, you're trying to change code.
Okay. Yeah.
That code will be evaluated against an evaluator function, right? You need to get increasingly better and better scores, and you don't have visibility into the evaluator function, right? You can just get the evaluation. You need to change your code in a way that you get increasingly better and better evaluation results, right? So this is an example. I mean, I don't really can't say that I understand. So this is what it came up with to solve the matrix multiplication problem, where it beat the Stassen's algorithm from 49 was able to get 48. And this is like this is the diff that was suggested. So initially there was no.
This one is the.
So
What's the evaluation? The only feedback it has is the evaluation, or other stuff it
No,
generates?
just the evaluation.
Just a number. It's a number.
It can be one number, it can be a set of numbers, but yeah, it's a numerical.
Because if it's just a number, it's kind of dumb. Like it's like parameter optimization. You just keep searching until you find something better, as opposed to having some tests that would say, for this test I have A, I have B, so now I have to multi-opposite, or I can go back and say maybe I can what's the intelligent part here? If you have more things that you evaluate, whether it's different numbers or something more sophisticated, then you can go back and intelligently change the input through going through the process again.
Yeah, I think this example might be helpful. So this is the
Basically saying the same thing.
yeah. Yeah, no, I get it. So this example is helpful, where what you're trying to do is you're trying to come up with a matrix multiplication algorithm with the least number of scalar multiplications. So evaluation metric becomes what is the number of scalar multiplications that you had to do a 4 into 4 multiplication, right? 4 into 4 matrix multiplication. So the evaluation function will just run a suite of 4 into 4 multiplications, and it will compute the number of actual multiplications that you did. And that's sort of the evaluation, right? Now, everything else, the program has come up with itself to figure out how to become better at the evaluation metric. So all this diff that is there. So this evolve block start is where I think so this is the full diff, right? So this is what we gave. I think this was part of the this thing, and then this is all the diff. So I don't really understand what it's doing here.
I can get my answer. I think probably there is, mathematically there are these values for parameters that are supposed to be found in some sense, and you would continually change them. So the structure of the code does not really change. But then the parameters which make the code, the formula itself.
Yeah, no, so yeah, that's right.
Tweaking them by very small margins.
Right. So this is probably heavily influenced by the heuristic. So you might be able to provide some sort of a heuristic to start with, and then it figures out how to play around with that heuristic. I don't know if it really works with a blank slate, right? I don't know if you can just start with return 0 and then figure out a program to do that.
So this seems like a very, very, very good almost cold start. You start with something, you give it to it, and just.
Yeah, like a slightly warm start. Yeah.
May not be better than the actual optimal, but it's so close that it's not worth for you traveling to actually picking. So you just have potential costs as your human costs.
But ideally, though, parameters are not changing here, right? The thing that is evolving is the prompt itself that you.
Yeah. So the prompt evolves and the program evolves. So the prompt looks at a parent program and comes up with a different program by applying a diff, right? The prompt is also evolving.
That is a response to that, let's say, that prompt to an LLM, and now that program is as a response of that LLM, right? Then
Right.
Another step of it, the prompt is also evolved.
Yeah. So the prompt that you give also evolves. The programs change every generation. So whatever the promising programs are, that goes into the context, and then the promising programs along with the prompt goes to an LLM. Out of the LLM comes a new code block.
Just one tangent here I want to bring, and
that commentary, like it's relevant to us. So it's this what we are discussing is more about scientific discovery point.
Yeah.
But there are various trivial tasks that we want to do while them, right? Let's say consider text to SQL for example. Now there's one way that we follow is fine tuning, right? We have
Yeah.
followed examples. But can it be somewhere where we are using this kind of methodology to come up with a more optimal prompt, right?
No, prompt नहीं है ना, ना मेरा भी वही understanding हो रहा था, लेकिन
But prompt is simple,
नहीं, ऐसा नहीं होगा. I think if you give it multiple iterations, तो will have an optimal text to SQL. Like तूने एक बार run किया, तेरा SQL आया, you send it to your evaluator. Let's say उसमें कुछ average की तेरी definition गलत है. This will go as a feedback to your prompt. This will again change your text to your SQL block. Again it will be evaluated and again ये एक loop में होता रहेगा.
Correct.
Now the most important part over here is your evaluation block.
No, but prompt is also getting changed, right?
Prompt is getting changed.
Prompt is getting picked up. It's not getting changed automatically.
No, so the prompt is also getting mutated. So
But so now you get
yeah.
you will get text to SQL. But now, as soon as you got the optimal prompt for text to SQL generation, maybe for that SQL you got an एक step by step करके तेरे पास आएगा. Is what I understand. Like it can take 4 steps, it can take 10 steps also to reach to the SQL. But there is not learning is not happening over there. Your model is not getting changed. The feedback is just कि your context is getting enriched now.
No, but there could be some point of discovery, right, where we crack the point कि okay, given this model, given this task, I now have optimal set of instructions in the process, which I can kind of relay every time.
I think
Some
what
chain
you're
of
saying is
thoughts-
should be possible.
Some kind of thoughts can be generated from this.
Because creating a prompt is also creating code only, right? You can also look at the prompt as being part of like the code. And so if you have a benchmark, so I think let's get back to this question when it is more relevant to this paper. But for Alpha Evolve, basically this is the last basically interesting part that I wanted to show is they at least did an evaluation study on one of the problems, which was matrix tensor decomposition. And what they show is they're doing a lot of things here. So they're using an LLM, they're using the context and meta, like there's a meta evolution of the prompt also. And they're doing a bunch of stuff and they're showing what are the key drivers. So the blue line here, it shows that if you don't use anything, basically you don't use evolution. So basically what you're doing is you're not storing those programs. So you're just iteratively looking at the results and trying to get the next best thing, but you're not looking at the promising inspirations from previous runs, right? Then you have no context. Then you have the LLM. So what if you don't use a stronger LLM? What if you use a weak LLM? Then this is no meta prompt evolution. So if you don't mutate the prompt, so keep the prompt the same, mutate the programs, but keep the prompt the same. So the biggest jump you can see is like between using evolution and not using evolution. So the biggest jump that you'll see, so all these lines are close together, but this blue line is far. So using evolution for at least for this problem made sense for them to store all these heuristics and then the ability to call on them and mutate on them was very useful for this problem at least. And everything else also marginally improves that using a better LLM, using meta prompt evolution, using full file evolution. So they also have a variant where you can restrict your diffs to a certain section, but then you have another variant where you can evolve the full file, right? So all these things make a difference, but the biggest difference is using this evolutionary approach of mutating programs, storing them in a database, and then calling upon inspirational programs from before. This is the kissing number problem that this thing, but they have not, for some reason, they don't have the evaluation for everything. So they have only no evaluation, no context in the prompt, and full method. So this is not, it's not as revealing. And so I think this is the time I'll just briefly talk about the AI co-scientist work. So I wanted to cover that paper, but basically the co-scientist work that Google Research came upon is also very interesting. But the biggest difference becomes the evaluation. So when you're solving computational mathematical problems, the evaluation becomes trivial. But when you're actually making scientific discoveries, and most of the things that the co-scientists targeted were new drug discovery, drug repurposing. So basically there's an already discovered drug. Can it also cure some other disease which is not being used for right now? New drug discovery and explaining the mechanism of action for a unknown biological phenomena, right? So these were the types of stuff that they really wanted to get at. And the biggest problem here, so the system is different in a way that you have a research goal from a scientist. There's a research plan. There's a generation agent which will generate more and more plausible hypothesis of. So basically, this is a hypothesis generation engine. So you can have multiple hypotheses that this drug can work on this disease. There's a reflection agent which will make sure that all the hypotheses are grounded in actual research, right? And they do sound plausible. There is an evolution agent. So this is again where you have a pretty so the theme of evolution comes in here is when you have a set of hypotheses, you look at previous hypotheses which have shown promise, and the notion of performance here. So you don't have an evaluation metric, and the notion of performance comes with agent tournament. So there's a ranking agent. What it does is if you have 10 hypotheses, it'll take two at so if you guys know how chess rankings work, like the elo score, right? Every hypothesis starts with an elo score of 1200. They are pitted against each other. So then there's a big tournament. At the end of the tournament, you have a ranking, but everything is done by an LLM, right? So eventually, this could all run into like hallucinations and go completely off the mark. And this is where this is only a co-pilot and not an autonomous agent, because you need heavy influence from the scientist to first of all ground the initial base set of hypothesis and keep on. So it keeps on discussing via the chat inference. So you can actually intervene if you feel that the hypotheses are going in the completely wrong direction. And at the end of the day, the best hypotheses that are produced, those, since you don't have an evaluation, those are eventually actually put in the lab to test, and that's how you can get feedback. So the feedback loop is also slower, but still they have been able to show that yeah.
When you have these tournaments, someone wins, someone loses. How do you define? How do you?
So an LLM defines it. So I'll put
Even the metric for that is defined.
Yeah.
And that metric stays the same for each tournament, for each round? Or?
No. So it's an elo score. So everybody starts with 1200.
Sure. Yeah.
And then the LLM does like matches. So
I just pairwise comparisons.
Pairwise comparison.
That's it.
Right.
It just guesses. There's no score. It just guesses.
There's no score. It just guesses which one wins. So in every comparison, there'll be one winner and one loser, just like in chess. Like, this can be a draw, but in this case, it'll be one loser and one winner. And then based on the tournament, the elo scores will get updated, and the highest elo scores will be like the programs. So in this case, hypothesis, not programs, which will get mutated to the next generation. Right. So there's a very heavy dependence on LLMs being grounded and showing good reasoning, and a dependence on obviously physical testing. So these are the couple of things that they were able to do. They were able to do drug repurposing for another disease. So a drug that was already there, it was suggested it can work for acute myeloid leukemia, and it did show in the lab some promise. This was the most promising one, is that they were able to, so the AI co-scientist was able to come up with an explanation for a biological phenomena, which took people sort of in the lab around 10 years of iterative research to come up with that explanation. They came up with that explanation, but they did not publish it, and it was not publicly available. So the LLMs did not have access to this. But in 2 days, the LLM was able to come to the same explanation. So this was the most verifiable outcome of this, because everything else, like they have done some lab tests, but it's not clear whether it will eventually make it to the drug, because that will take more trials. But this was the most immediate feedback, is that there was a known explanation which the LLM could not have known, but it was able to, obviously it built upon all the literature that they would have already done. It's not that the 10 years of research was invalidated. It built on that, but it was able to come to the same explanations. That is one of the major breakthroughs.
It was repurposing the research, found a drug.
No. So ये वो वाला नहीं है. So found a drug and repurposing were also promising, but उसके लिए they tested in the lab. They can verify that there's some promise, but not till you have human trials and all that. You cannot confirm. But one of the tests that they did was,
It was promising.
why are this so? Explain the mechanism of why this is found in some bacterial species. So this is a clear explanation. There's a right answer that they already knew, but it was not published anywhere. And it took them 10 years of iterative research to get to that answer. But this AI code scientist over 2 days was able to get to that same hypothesis.
EML has a very high fatality.
Right?
Of course, it's not 10 human days, and we don't even know how much actually compute they used. I think.
And is it only one hypothesis, or they generated like?
So they generated a lot of hypotheses, and this was one of, so when you have the ELO rank, right? So at the end, every hypothesis has a ELO rank, and this hypothesis was in the top 10 ELO ranks. Right? It was not the first one. I think it was the fourth or third or fourth one. So it's not the only hypothesis, but it was one of the right hypothesis of one of the top 10 hypotheses, which is also a good enough outcome. Right? The last paper again. So this is all work happening in separate. This is work happening in Japan, all the way in Japan. But then
It's a little tricky in that it generates a hypothesis and it ranks this one at the top or maybe close to the top.
the fourth.
Fourth, but someone could have come up with that hypothesis on the very first year, but proving, did it come into that, you see what I'm saying?
Yeah.
Was it coming to the conclusion 10 years or coming to the hypothesis 10 years? It's not the same.
So this is not technically a hypothesis. You did ask the scientist for an explanation for something, right? And then whatever was the most plausible explanation, it ranked and did all that stuff. So it offered an explanation. It offered 10 explanations, right? With decreasing confidence scores. The explanation that it had the fourth biggest confidence on was in fact the right explanation. But there were 3 explanations before that also.
Sure.
So this is not something. I mean,
Yeah, I don't question that.
Yeah.
From the scientist's perspective,
of course, yeah.
what does it mean?
So it means that you can probably
Was it
generate.
took 10 years to verify or take now 10 years to come up? 10
I think
years
to verify. I think to verify.
So that's the misleading part.
Yeah. No, you're right.
Can't call it a hypothesis. It's most of an explanation.
Explanation. Yeah. This one was an explanation, and yeah, this was a verified explanation in the lab, but it was also one of the top 10. So in that sense, it's interesting. But yeah, it's not fair to say that it actually came up with it because this was not the only explanation, and
Top 3 explanations are also not
also there, right? And then eventually you have to verify.
You have to verify.
So again, this also points to like why this is an AI co-scientist, and this points to
Yes.
like the limitations of solving problems where verifiability is an issue, right? Where there cannot be quick feedbacks or clear evaluations, right?
But at least reduces the search space.
The search space, yeah. So
If you verify only what is more likely, and then
yeah,
you would have
yeah.
taken
So it can do a lot of literature review. It can ground all the hypotheses in this thing. It can reduce the hypothesis space and stuff like that. But still always be enabling and not like until the time you can formulate the problem as a very close form problem where you can any given solution can be evaluated like mathematically. It doesn't not become autonomous.
So also it should be consistent, like across different problems, it was able to come up at least top 10 वाला match कर.
हाँ, right.
So
So
you will be always uncertain कि
This is a thing check like एक ही दिखा है एक पे चला है.
हाँ एक पे चला है then.
No.
and this is like the last paper. So this also came up. I think this came up just last week. And this is Darwin Godel Machine. And a Godel machine is basically a self-improving machine. It was a mathematical concept that was introduced 50, 60 years ago, where it was self-improving in the sense that the idea is that every change that the machine makes, it should be able to verify if it's an improvement. Right? That's a Godel machine, so it can improve that way. But what these people claim is that that's a very strict requirement. You might not be able to prove that the improvement or mutation that you've suggested is better, but you can still provide empirical evidence. So what they essentially do is they use some software development benchmark. So for example, I think the main one they've used is SWE Bench and Polyglot. And what they do is they basically had, there's a coding agent which has the ability to change its own code and its own prompts, right? And it can change its own code. Then it goes into the evaluation where it is evaluated on all these benchmarks, and it can print its own logs of what is the thing it's trying, what are the outputs, and it will also be offered, of course, what is the final evaluation. And so based on this, you have something like you will mutate and build something like a tree. So you start with, let's say, the initial coding agent, which is, let's say, a very basic agent. Then what you will do is you will propose mutations to this agent. So the agent will be able to, let's say, use an LLM to apply diffs to its own code. The resulting children, some of them will not even be functional. So they will not be able to even run the code. So it will not even run basic tests. So those are then eliminated. Some of them will be, then they'll be evaluated, let's say, on SWE Bench, right? And then those become part of like the program database and the inspiration. So this is very closely related to how AlphaEvolve works. and then you'll have the next generation, and every time. So the good thing about this is you actually have. So this is actually a paper, and you actually have the mechanism. So you actually have the full algorithm of how this works.
And plus इसमें बहुत clear है, like it is changing its own code.
It's changing its own code. हाँ.
There is no room for guesswork.
Guesswork, correct. So you can actually, and this is basically the algorithm. Is you start with the initial agent, and T is, let's say, how many generations of evolution that you want to go through. Every time you sample some parents, right? And the sampling strategy is here. Essentially, basically sampling is proportional to performance, how you did on the SW benchmark. It's also proportional on how many children do you already have. So something that doesn't have a lot of children will be preferred because of diversity, right? So you have a novelty bonus, right? You have a performance bonus, right? And then you normalize the scores, and this can remind you of like GRPO, where you actually have. So that you provide the stopping. So you tell how many generations of evolutions do you want to do. So the depth of the tree, that's something you can control.
Then from all the leaves, then they choose the best one according to these metrics.
Right. So then for each parent, you do a small modification. It's in an LLM, right? So the program will evolve itself. It will evaluate itself. If the outcome is a valid thing which can run code and self-modify and has basic functionality, it will then be added to the database, right? And the interesting thing in this graph specifically, so this is the best agent that they were able to come up, the star one, right? But obviously the path went through a lot of low performing agents, right? And at any time, at any time there is a fair probability of any of these programs. So most of these programs stopped having children because they were very low performing, and they had although there is almost never a zero probability of a parent getting sampled, you started to see more and more children here because the performance in this part of the tree was much better, right? And then you can see the scores going up with the depth increasing.
But this may be like here, like it's we who actually define where to stop. Like considering the black children's, we are making them stop, but it may happen unless until they try that from black children, if they go further.
No. So the black children are programs which have completely lost functionality. So they are not even running code right now. So they are just eliminated, right? So those are not functioning agents anymore. So
why is there a 50?
आगे जाके future में they might get a much better than what is the best one currently because they have a
But as you go down a tree,
Higher on the benchmark itself. That's why benchmark.
So it's greedy. It's not greedy in the sense that after any generation, the probability of sampling any of the functioning heads is non-zero, right? So let's say when I was here, I could have actually sampled this program to evolve also, right? Yeah. But so in that way, the exploration part is already there. But yes, as the probability of sampling a promising parent is higher.
Yeah, right.
So it's not strictly greedy, but it's like some exploitation that's happening.
This is not free, right? This is just a visualization of the actual, like, a representation of what could be the actual tree.
no.
Sorry?
Is that all the spaces that were shared? This is the entire tree. For the first node, if you look at the left hand side, there's a green there. On the left hand side is
36
or 36. It wasn't explored.
leftmost not 30.
Yeah.
It could be because sampling probability didn't allow it to be sampled.
Yeah, effectively, yeah. Right. So this is one realization of the tree. If you run this again, you might have a different tree. Right. So this is one realization of the tree.
So when does it actually modify its code in this tree? Like how does it?
So if you look at the algorithm, first you select some parents using that sampling strategy, right? So there's a set of every green node on that tree let's say I want to evolve for another generation. So every green node on the tree is a parent, a potential parent. You will sample, uh, some parents from that tree, and each parent will then self-modify. Right? So each parent will basically have a history of what are the self modifications it has already done, all the logs that it has generated while running the evaluations, and obviously its own evaluation scores. It will use all this context to self modify its own code.
So it's actually modifying the code in the database, but it's not modifying its own code. Right? So this algorithm one will never get modified, basically.
So you mean, so yeah, it's adding another node. So basically it's modifying code and then creating a new node.
Right. So, but it's almost the same as alpha evolve, right?
Yeah. So it changes its own code in the sense that a parent's code is changed and then it becomes like
Oh, I see. So the
yeah.
history is not retained
Um,
of the
history
parent.
it's retained in the context, but apart from that, obviously this code is pretty stateless.
Mhm.
So what this is a particular, let's say this is a particular commit. You'll have ID for this code, and this code is unique. And then 24 will have another commit ID.
Right.
Is there a reason why the best after the best solution there was no anything, no child?
So you mean 56?
No, after 56 you have the best solution, but
No,
after
so I think 56 is the best solution, I think. No, I think 64 is the best solution. Yeah.
so yeah, why was there nothing else?
So it's restricted by like the by you basically. So you basically put a constraint on the number of evolutions that you're willing to allow. Right. So this is not the best solution. This is the best solution till the time that you allowed it to evolve.
Or maybe like a downstream task based, like we using polyglot or SDs benchmarks. There's a threshold whichever solution reaches first, maybe we stop there.
Yeah. No, I think in this case it's pretty.
Run it for those number of evolutions regarding
Yeah.
whether we have
So there's no early stopping. That sort of stuff is not there, right? And so this is a similar ablation study to what we saw on Alpha Evolve. Is so there are two variants that they have. One is what if you did not do open-ended exploration? Is basically when you were evolving, what if you didn't have that inspiration part? So you don't look at other successful programs. So let's say you don't do that. You don't maintain that database. You only look at the current code, right? And you try to improve that code. You don't have any inspiration from other programs. So what happens if you do that? So basically, the open-ended exploration is not there, and this other is self-improvement. So what the program can also do is it can also right now the program looks at the current code, and it also has a rich context of how you arrived at that code and what are the logs that are generated when you are running evaluation. So what if you remove all that? You just give the current code, right? And you give it whatever evaluation you have run, and that way that it can't really self-improve because it doesn't have the context of how I got here. So what happens then? So both of these ablations they have done. So basically a lot of jump you're getting from self-improvement. So if at evolution time you have a history of how we came upon these changes and what were the logs that I generated, that gives a massive jump in terms of how far you can go. And obviously the open-ended exploration also helps. Right. So these are the two aspects that the self-improvement and the open-ended exploitation, which means like you maintain a database of programs which can share inspiration with each other. So both of them contribute, but the biggest contribution comes from the self-improvement factor.
self-improvement, the same path, this chain of nodes, and
Yeah.
I'm sorry. Forgot you. Is anyone raising a doubt or something? So, Dhruv, I had this question. Basically, the sampling strategy in this paper, Darwin Godel Machine. This looks like the basic thing. Basically, whichever program or half-baked program is giving us the higher score, the sampling probability of that is high, right?
Yeah.
Compared to in the alpha evolve where we are keeping the database, there how they are sampling the programs. Is it also in some way that the half-baked program which were scored high on our hypothesis, those are sampled, or it is based on the new strategy that we are choosing?
No, no. So I told you like the sampling strategy. So they mentioned a couple of algorithms. One is the island algorithm and one is the map elites algorithm. So these are
Right.
evolution algorithms which come up with their own sampling strategy. For the island algorithm, you have like say a bunch of 10 islands, and you always sample the elites from each island,
Right.
right? And in the map elite algorithm, you divide programs by behaviors, and for each behavior you look at the elites.
Right. And these database अगर इसको बोलते हैं तो is it stored in the separate memory, or is it just part of the long prom?
No, this is stored in separate memory, then it is queried and then put in the prompt. Like whichever programs are sampled, they are put in the prompt as an inspiration.
Got it. I think there is there is one more solution which talks about the similar thing. There is a package called DSPY. Uh,
Okay,
so-
bro, I'll have to vacate the room.
Oh,
Yeah.
okay. Sorry.
मैं Slack पे मैसेज करता हूँ.
ठीक है. Okay.
मुझे लगा कि